Hi, my name is Tyler Steffen, and this is part two of my applied machine learning term project, where I will be trying to encode wave packets inside of the latent space of convolutional autoencoders. Just a general project overview and the goal. We have a 1000 by 1000 complex valued field, which is essentially a million 64-bit complex values, and we want the model to compress it into the bottleneck latent space, and we want this latent space to entirely represent the original million point value. So the latent space can be really useful because in that small bottleneck of information, you can study a much smaller number of variables and hopefully attain like more meaningful information from it. And also, you can say you're compressing the latent space down to 64 uh, floating point numbers. That's then a 64 dimension vector, and you can randomize the 64 dimension vector, you'll put it into the decoder, and you have a generative model. So this is really, really appealing, and getting it to the point where you could generate other likely wave functions would be very useful. For this specific project, I started with the goal of training the model on a single wave packet. So only one small Gaussian wave packet was put into the input fields. And th- this hopefully created a very simple situation where there are only about 5 input variables, 2 for the direction, 2 for the position, and 1 for the actual size of the wave packet. And ideally, this would have then compressed into 5 latent space dimensions that describe the vector. Now, in practice, this is not so easy, and I'll get more into that in a bit. The existing body of work that I looked at for this is really the same as the first part of the project. The only huge difference is that there was a lot more existing work that I was able to draw from, especially based on Steve Brunton's stuff, because autoencoders are extraordinarily popular when looking at physics informed machine learning tasks because the latent space is just so descriptive of what the physical situation is if it's parametrized correctly. So, mostly just the fact that there is a lot more examples of people doing what I'm trying to do here. So, I basically mocked up the entire model and several different versions of the model inside of Excel. I built this sheet because it made it a lot easier to look at what the next layer's rows size would be quickly and iterate and make changes quickly, as I could just place in numbers to the kernel and stride attributes and I would instantly see results and my graphs would instantly change. And I'll walk through that a bit in the code walkthrough. But I basically used this to quickly iterate and come up with a few models that looked somewhat viable, and then I was able to test those, and some of them did end up working. But I think the most important thing to pay attention to here is just this area, the bottleneck, because as you can see here, lots of information coming in, and it even gets expanded here to try and allow for some abstraction in these wider layers here, and then it bottlenecks down into the latent space. And that is where the valuable information is hopefully being trained and learned. All right, now looking at how I actually implemented the model. So this is the model, the encoder. I actually have several different versions of this I've tried, but this was just the one that's kind of pictured in that spreadsheet there, where this parameter here is just an integer that determines the size of the latent space. And I scaled this all the way from 1 to 16, and you'll be able to see the results of that. These are just some simple helpers that I used because in my first project, I built a lot of custom complex neural network architectures, which great. I tried to build some for this project, but I was having a hard time actually getting them to work. And well, they would run, but I had a hard time actually getting them to optimize. But that's a whole nother thing. So the easier thing that I found to do was just split complex into 2 channels. The network will figure out how to handle that information. It's not worth trying to deal. It probably is worth trying to deal with. I just haven't figured it out yet. And then here's the actual training loop. The big thing to note here is I don't have a set training set or data set ahead of time, obviously, because this is just generative stuff. I'm using this basically as my guiding function, which is just it's the same sort of field wave packet generation that I used last time, except I'm only ever generating one particle and putting it into the field, and it's just randomized position, size, and direction of the momentum vector. All right, now looking at some results, the first thing that I really used to test the model and validate that it was at least doing something correctly was a straight run of putting a generated wave packet that I generated with my classical methods into the front end of the encoder, and then see how it actually like through the entirety of the model. And this is a completely auto-encoded wave packet, and this is a completely auto-encoded wave packet. And what I've done here is taken this, ran it through the encoder, taken this, ran it through the encoder, created a line space in between them inside of the latent space, and then these are interpolations of these two wave packets together. So you can see it fades between them as you cross through the line. And so this is it's behaving somewhat as it should, but this is not really ideal. Um in comparison, and you can't see these do technically have direction, but that's going to be encoded in the complex part of the field. You want this is the absolute value. So what would be more desirable than this fading between the two of them, almost like they're weighted, would be instead if this one here moved, rotated, and scaled as we went through the line space to move, rotate, and scale into this one's position. That would be what I would expect if I'd condensed the autoencoder properly down to that 5-dimensional latent space that I'd talked about. And you can see the issues highlighted even more so here, where I tried to generate a random vector in the latent space, not associated with any of the input encodes, and it just looks like noise. So there's still a lot to be done there. The entire latent space isn't well covered with valid wave functions, which makes it such that things like this happen. You go into your latent space and you don't get a valid wave function out because only certain parts are recognizing as valid wave functions currently. I think part of the issue is maybe not sufficient training, but also you'll be able to see pretty quickly here. This is my training loss, and you can see from left to right, it's increasing in bottleneck size. So this purple one at the bottom is the largest bottleneck, and the red one at the top is the smallest bottleneck. And what you can see is the red one takes a long time to start going, to the point where this is 2000 epochs. This had just started this sort of downward trend that you can see in the rest of them here, where they have this secondary downward trend. So I think more training time could be a positive, but this is already very intense. These are 20-minute simulations or 20-minute train runs on a very on very high-end hardware running at 300 watts. This is not cheap stuff to do. So I need to figure it out a bit more before I continue doing this. And just generally looking at where I want to go with it in the future, I think these are satisfactory results to start with. I'm starting to show that I'm obviously compressing into a latent space and getting what I want out, but it's not as compressed as I'd like it to be. I think it can obviously get much further, considering how much information goes into making the system in the first place is nothing. So I think there's a lot to be changed there and improved there. And how I want to do that specifically, I have a very concrete idea, is I just want to train the encoder to encode the exact parameters that I generate the wave packet with. And hopefully if it could encode those 5 parameters, then I could reattach the decoder and then have the encoder not change at that point and just train the decoder to take the encoder's output and correctly. And at that point, it's like, why are you even using an autoencoder? But I think the interpolation is still really interesting, and especially considering how wave functions can combine in quantum mechanics to make other wave functions, it's I think has some direct use to the field. Once again, that's just my page for the library that I'm working on, which is Berry physics and machine learning combined together, and that will be what I continue to work on over the summer. All right, and then just real quick, this is the Excel sheet which I use to sort of build out the model and design it by looking at the information in it, and it's something that's pretty quick to just go through and prototype. So this turns on layers, so there's like I could obviously make this bigger, but there's 15 in the encoder and 15 possible in the decoder. I only have 4 each right now. I can turn them on by putting ones in, and you can see more values get added to the layers over here. But really, I don't want that. But this is just a very useful tool that I use to kind of figure out the models. And now looking at the actual model and the training code. So this is the model that I actually used. And those are these custom implements I use to handle the complex. These are complex layers I was trying to implement in the past. I really wanted to, so this is a completely complex convolution layer. The one that I want to include more and really is just, as I've thought about it more, could be brought about basically with dilated convolutions, but a some sort of multi-dimensional Fourier. In this one, I was just using a two-dimensional Fourier, waiting in the middle, and then doing an inverse Fourier. So that it's I wasn't able to get this to work, but I really think that if I'm able to introduce some more spectral stuff into the actual architecture, that it will be very beneficial considering the spectral nature of quantum mechanics. These were other architectures I tried to run where I was just like cutting out the middle layers to make it wider, and um it says hybrid autoencoder. It really is just a convolutional autoencoder. The goal was to make it Fourier and convolutional layers combined, but that obviously didn't work out yet. Then this is what it these hybrid layers are concatenations of a Fourier and a convolutional layer. So over on the right then, we've got our training loop, and this iteration here is just how I ran a bunch of different bottlenecks and took all those losses so that I could get that data out. It's just looping through training a model several times. Inside the actual training loop, I have several different outputs. So like this is the one side of the interpolation, this is the other side of the interpolation. This function actually does the random noisy field that I would like to be a more defined wave packet, but it's not yet. This part, the guess fields, calls this interpolate fields function, which is this is what's taking in those 2 points in the latent space and then creating some interpolation between the points in the latent space. So that's what was generating those kind of fading particles. So then lastly, just looking at the loss, which was a hugely important part of this project. First off, we have a complex field, so getting it to Torch doesn't provide a default complex MSE loss, so I had to implement one myself. This one, technically, you could have taken the average of this, but I wanted it to be very strict, and I want it to sum every. I want it to capture any error that exists. So I just sum it, and I know this is a much larger number than most losses, but as long as it's balanced with the other parts of the loss function, I don't see it as a problem at all. Um, this part is trying to detect the highest magnitude spots in the field and check how many other spots are of a similar magnitude to that one. And what that hopefully does is maintains how many particles are actually in the field. So if you have one particle in the field, your autoencoder output's also going to have one in the field too. It's just a simple sort of counting mechanism that adds an extra piece of the loss that hopefully accounts for those spots. Otherwise, I think that is it. I did experiment with other losses, but did not have luck with them. They gave me very odd results when I was using. There's a You can use Porch's structural assessment functionalities, and I was not able to get good results out of it. But I'm excited to keep working on this, and thank you for watching.